The last review problem is a spring mass system that is going to be in a damping fluid or damping medium. So this problem is number 25 from the ZIL textbook on page 207, and I'll just read the problem and then solve it. A force of 2 pounds stretches a spring 1 foot. A mass weighing 3.2 pounds is attached to a spring. The system is immersed in a medium that offers a damping force equal to 0.4 times the instantaneous velocity. Part A says find the equation of motion. The mass is released from rest 1 foot above equilibrium. Part B, put the equation of motion in phase amplitude form. And part C, by the times at which the mass passes through equilibrium. So let me write down a few key numbers. And then we'll first find the equation of motion using Newton's second law. We're going to go ahead and derive that, which is something that you should be able to do. So the fact that the force of 2 pounds stretches the spring 1 foot is going to allow us to find the spring constant, K, in Hooke's law. And so we know that K times the stretch is equal to the weight, and that's what we get from Newton's second law when the mass is in equilibrium position. So K actually equals the weight, which is mass, times gravity, acceleration due to gravity, divided by the stretch. So our spring constant is the weight, 2 pounds, divided by the stretch, 1 foot. So the spring constant is 2 pounds per foot. We also are going to need to know the mass of the object, and we were told that the object that is going to be in motion is a 3.2 pound mass. So we know that the weight of the object that we're going to be modeling is 3.2 pounds. Weight is mass times gravity. So we do know that mg equals the weight. And we know that the acceleration due to gravity is 32 feet per second squared. So we can now solve for the mass. And the mass is going to equal 3.2 divided by 32. And if we simplify that down, we're going to get 1/10. 3.2 is going to be 1/10 of 32. So we also know that the damping force is equal to 0.4 times the instantaneous velocity. So that tells me that beta is going to be 0.4. Okay, so let me go ahead and set up, I'm going to just write down K, M, and beta, and I'm going to derive the differential equation that will give us our equation of motion. So K is 2, M is 1/10, I'll write that as a decimal, and beta is 0.4 as a decimal. So we need to use Newton's second law. We've got the spring, we've got the mass, and we've got it immersed in some sort of solution, the entire system. And we're going to call the equilibrium position x equals 0. The mass is moving up and down from this equilibrium position. So x of t is the distance of the mass at time t from equilibrium position. And remember that we consider the downward direction to be the positive direction. So if we use Newton's second law, which says the sum of the forces on an object is equal to the mass times the acceleration of the object, we can derive our differential equation that will allow us to find the equation of motion. The forces acting on the mass are gravity acting downward, and the force of gravity is m times g. And then we have the spring force acting upward, so F sub s. And we also have the damping force of the fluid. The damping force is going to act in a direction that is opposing the motion of the object. So the forces, if this object is moving down, the damping force is going to be pushing up, pulling it up, pushing against it in the upward direction. So the forces that we have are the damping force, the spring force, and the force of gravity, and that should end up equaling the mass times the acceleration of the object. We are going to let x of t be the position of the object at time t. That means x prime of t is the object's velocity at time t, and x double prime of t is the object's acceleration at time t. So the damping force is actually equal to negative beta, whatever the damping coefficient is, times the instantaneous velocity x prime, plus the spring force is k times the stretch in the spring, and since that stretch is going to change as this object moves, the total stretch is going to be the initial stretch to equilibrium position plus however much the object has displaced from equilibrium at time t. And then we have mg equals mx double prime. And on the left-hand side, we're going to get, oops, I should have written this as a negative. The spring force is going to be a negative k times s plus x. Because gravity is pulling down. If the mass is down here, gravity is pulling down, and the spring is pulling up, and the up is the negative direction. Okay, so we can substitute in what we know. Beta is 0.4, negative 0.4 x prime, minus the spring constant is 2. Actually, the stretch, s, you can plug that in, or the other thing that's going to happen, let me just simplify this before I plug in. Negative ks plus mg is going to be 0 because the spring force at equilibrium is going to be exactly equal to gravity pulling down, so those will cancel. Negative beta x prime minus ks minus kx plus mg equals mx double prime if I just distribute. And the negative ks and the mg will cancel because those forces are in balance when the object is in equilibrium position. If I move the other two terms onto the right-hand side, actually I'm going to switch back to black. I'm going to get, actually let me write mx double prime, and then I'm going to add plus beta x prime, and then plus kx, which would mean I'm moving those terms over to the same side as mx double prime. I do know the mass is 0.1, so I get 0.1 x double prime. Beta is 0.4 x prime, and k is 2, so 2x equals 0. And I'm going to multiply everything through by 10 just to avoid decimals. So the differential equation is x double prime plus 4x prime plus 20x equals 0. Okay, so I need to actually solve this. It's a constant coefficient homogeneous differential equation. And so I can use the auxiliary equation, which is going to be r squared plus 4r plus 20 equals 0. Whatever those r's are, my solutions are going to be e to the r times t, because x is a function of t. So let me write down the auxiliary equation next. So to solve this differential equation, x double prime plus 4x prime plus 20x equals 0. I will assume the solutions look like e to the r times t. That will give me an auxiliary equation that looks like r squared plus 4r plus 20 equals 0. And then I can use the quadratic formula. That doesn't factor real nice. So using the quadratic formula, I'm going to get r equals the opposite of 4 plus or minus the square root of 4 squared, which is 16, minus 4 times 1 times 20 over 2 times a, which is 1. And then r is going to be negative 4 plus or minus 16 minus 80 is negative 64 over 2. And so this is going to be negative 4 plus or minus 8i divided by 2, or negative 2 plus or minus 4i is the solution. So these are complex roots, which means I'm going to get sines and cosines in my solution. X of t is equal to, when we convert these e to the complex root times t using the Euler identity, we actually get sines and cosines. So it's that form that we prefer. So we get e to the negative 2t times the cosine c1 cosine of 4t plus c2 sine of 4t. And so I still need to solve for c1 and c2 to get the equation of motion. I'm going to use my initial conditions to solve for those. We were told that the mass is initially released from rest at a point 1 foot above equilibrium position. So that tells us released from rest, the initial velocity is 0. So I know that x prime of 0 is 0. And the initial position is 1 foot above equilibrium, which is a negative 1. Using those initial conditions, I'm going to solve for c1 and c2. So I'm going to first use the derivative initial condition. So x prime of t is actually equal to, t is a product rule, so the derivative of e to the negative 2t is negative 2 e to the negative 2t times c1. You know what, I changed my mind. Let me first solve x of 0 equals negative 1. And negative 1 is equal to x of 0, which is e to the negative 2 times 0. c1 cosine of 0 plus c2 sine of 0. The sine of 0 is going to be 0, so that term becomes 0. And I get negative 1 equals e to the 0 is 1, and cosine of 0 is 1. So I end up with a c1 is equal to negative 1, and then I also need to solve for c2. So now I have that x of t, different color, x of t is equal to e to the negative 2t times c1, which was negative 1, cosine of 4t, plus c2 sine of 4t. Now I need to differentiate and use the velocity, the initial velocity. So x prime of t, the derivative of this first function is negative 2 e to the negative 2t times the second function, negative cosine 4t plus c2 sine 4t, plus the first function e to the negative 2t times the derivative of the second function. The derivative of cosine is going to be sine, and you're going to have a 4. So it's going to be cosine. Actually, cosine is negative sine. So negative of a negative, you're going to get 4 sine of 4t. And then the derivative of sine is cosine, and I'm going to get a 4 plus 4 c2 cosine of 4t. I get. So we're going to finish solving for the constant c2. I've taken the derivative of x prime of t, and now what I need to do is to use the initial condition that the initial velocity is 0, so x prime of 0 is 0. So I get 0 equals x prime of 0, which equals plugging in 0 for t. I'm going to get a negative 2 times e to the 0, which is 1, negative cosine of 0, which is going to be a negative 1, plus c2 sine of 0, sine of 0 is 0. So I get a 0 there. Plus e to the negative 2t is going to be e to the 0, which is 1, times 4 times sine of 0 is 0, plus 4c2 cosine of 0 is 1. So that all simplifies down to a positive 2 plus 4c2, and that's all equal to 0. So that is going to give me that 4c2 equals negative 2, where c2 is negative 2 over 4, which is that c2 is negative 1/2. Okay, so now I've got c1 and c2, and I can substitute those back into my original equation, which was x of t is equal to e to the negative 2t c1 cosine of 4t plus c2 sine of 4t. And then I'm going to have the solution, and I'll put it into phase amplitude form. So this becomes e to the negative 2t. c1 was negative 1, so I get negative cosine of 4t. And c2 is negative 1/2 minus 1/2 sine of 4t. Okay, so for part B, to put this differential equation into phase amplitude form, the amplitude is going to be the square root of c1 squared plus c2 squared. So it's just the sine and cosine part that I'm changing into phase amplitude form. The e to the negative 2t factor will stay the same. So c1 is the coefficient of cosine, so I get the square root of negative 1 squared plus c2 is going to be negative 1/2 quantity squared. So that becomes the square root of 1 plus 1/4, or the square root of 5/4, or root 5 over 2 is the amplitude of the sine cosine portion. The phase shift phi is going to be, we know the tangent of phi is c1 over c2, where c1 is the coefficient of cosine. So this is actually equal to a negative 1 over a negative 1/2. Remember, tangent is y over x, so this tells me that my phase shift phi, that angle, is in a quadrant where y is negative and x is negative, and that would be quadrant 3 in the Cartesian plane. Okay, so I actually can draw that angle in. That is actually not going to be any special triangle. If I have y negative 1, x negative 1/2, it's not going to be a 45, 45, 90 because the legs aren't the same. It's not going to be a 30, 60, 90 because the long leg isn't root 3 times the short leg. Okay, so we're actually going to have to use a calculator, and I need to find, if I simplify and flip this to negative 1 times negative 2 over 1, I'm going to get positive 2. And phi is actually just the inverse tangent of 2. So if I use my calculator, I'm going to get 1.11 radians. But that is actually an angle in the first quadrant, because remember this 90 degrees is pi over 2, which is 3.14 over 2, so that's about 1.5. So this angle, 1.11 radians, is in Q1. So in order to get the same reference angle, but to be in quadrant 3, remember the reference angle is the angle with the x-axis, I actually need to add pi. So my real angle, let me call this angle phi prime. My actual angle is going to be phi, so the top here. Phi is equal to 1.11 plus pi, which is approximately 1.11 plus 3.14, which is 4.25 radians. So my phase amplitude form is going to look like x of t is equal to e to the negative 2t. That part, the exponential part, does not change. And then it was negative, sorry, I'm not doing the cosines and sines, but it's going to be a times the sine of omega t plus phi. And I need to plug in my a and my phi. A is root 5 over 2. E to the negative 2t, root 5 over 2, sine of 4t plus 4.25. And this is x of t. Now that I'm almost done with this, I think this may be actually the same example that I did in class. Let me go ahead and finish the last part. This is the equation of motion in phase amplitude form. The last part was to find the times at which the mass passes through the equilibrium position, which means I need to find t such that the position x of t is 0, which is the equilibrium position. So that means x of t equals 0, so I'm going to have e to the negative 2t times root 5 over 2 sine of 4t plus 4.25 is equal to 0. I can divide both sides by e to the negative 2t root 5 over 2. And that's going to actually go away, and I end up just with 0 is equal to the sine of 4t plus 4.25. And then I can take the inverse sign. So I get sine inverse of 0 is equal to 4t plus 4.25. So if I'm trying to think of the angle that has a sine of 0, well, 0 has a sign of 0, right? If you're thinking of the unit circle, and the sign is y over r. You get 0, if your terminal angle, your angle is 0, you get 0 over 1, which is 0. I'm also going to get a sign of 0 if my angle is pi. So if I am over here, with my terminal side on the unit circle, then my y is 0, and my distance from the center is going to be 1 on the unit circle. So y 0 over 1 is going to give me 0. So every time I hit 0 or pi, 0 or pi, I am going to get a sign of 0. So the left-hand side should be all multiples of pi. And I'm just trying to make sure I get all of the places where the mass passes through equilibrium. Because the mass is doing some sort of behavior where the amplitude is damped down by this envelope. And so there are going to be many times where it passes through 0. So those times are going to be multiples of pi. So I'm going to write in pi for the sign inverse of 0 is equal to 4t plus 4.25. Then I need to solve for t. And I need to make sure my times are positive. So if I solve for t, I subtract 4.25 and divide by 4. That is t. And I need to know what n should be. N is going to be whole numbers, but I need those whole numbers to be such that I'm getting positive times. So if n is 0, I get a negative time. If n is 1, I get pi minus 4.25, which is negative. If n actually equals 2, I get 2 times pi, which is 6 point something, which is going to be positive. So the times are n pi minus 4.25 over 4, where t equals 2, 3, n equals 2, 3, and so on, bigger whole numbers. So anyway, sorry this is the same example, but maybe it helps anyways as a review to just see it again. And so that's the final example with the damped spring mass.